All right, welcome back. Happy April Fool's Day. I hope all of you have typed com.google into your web browsers. Everybody done that? If you haven't, you ought to try it. It actually works. It's pretty amusing. Don't do it now. You can do it after class. We're actually going to cover a lot of topics today. That's not an April Fool's joke, but we'll see what we can do. I did want to remind you briefly about memory mapped I/O that we talked about last time. So this was an example of a display controller. And basically the idea is the hardware controller maps registers and other memory on the card into the actual physical address space so that the processor can access it with loads and stores rather than something specialized. And in the really old days, you had to use hardware jumpers to get these addresses so that different cards didn't collide with each other. But now the ACPI layer basically does this at boot time. So for instance, just writing to display memory might change the image on the screen. This is the simplest thing to imagine if this is just a bitmap. We talked about how writing a graphics description in the command queue followed by, say, a write of the command can actually render some triangles. Etc. So basically, we do all of our control through loads and stores, and we can protect this with address translation to prevent the user from getting at devices we don't want them to. Were there any questions about this? Okay. We also talked about two different types of transfers to and from an actual I/O controller. One was called programmed I/O, and this is literally the processor is busy doing one loop per byte that's being transferred. Okay, so you're literally grab the first byte, grab the second, grab the third, and this is great for really simple things, but unfortunately it consumes processor cycles proportional to the amount of data you transfer, and so by the time you get to something big like a disk drive, which block device we're going to talk about today, you want to get access to direct memory. You want to use direct memory access, where all the processor does is programs the channel and the underlying hardware does the transfer for you. I showed you this idea here. I'm not going to go through it in great detail, but the CPU sets up the DMA controller and the disk controller so that data will get transferred automatically from the disk controller to the memory, and there's no involvement of the CPU after this is started and until this process terminates with an interrupt. Were there any questions on this? Everybody understand the distinction now between programmed I/O and direct memory access? Okay. Good. So today I want to discuss performance. We're going to talk about disks and SSDs, and we're going to pop in some queuing theory, and then we're going to start on some file system discussions as well. And so we'll see how this goes. But let's start with some basic performance concepts which we start wanting to think about when we're talking about I/O. First of all, the notion of response time or latency is the time to perform some actual operation. So you might say it takes 100 milliseconds or a second. Bandwidth is the rate at which operations happen, and that tends to be in, megabits per second or something like that, all right? And notice, by the way, that bandwidths tend to be in units of 10 to the something, whereas data, when we talk about a kilobyte of data, that's what? What's a kilobyte of data? How many bytes? 1024, okay? So data sizes are typically in kibes or whatever, the 2 to the something unit, whereas bandwidths tend to be in 10 to the somethings. And so this is something to keep track of when you're looking at sizes, okay? Now, startup overhead is another time which is part of the latency, but it's something that's often forgotten. So when I go and ask a device for some data, that latency is not just the time to pull the data out of the device. Often there's extra time involved in the queuing, involved in controller overhead, involved in moving the heads of the disk, and then there's the transfer time. Okay, and so people often forget the overhead when they say, well, latency and throughput are inversely related to each other. Well, they're not, because that bandwidth is sort of the tail end of the actual access. Okay, and I want to make sure we are clear on that. So basically, most operations are roughly linear here, so that latency is overhead plus the total amount you're transmitting over bandwidth. And notice that, yes, we are going to require you to balance your units. You can bet that there's going to be, in one of the two remaining exams, midterm number 2 or the final, there's going to be some case where you have to turn milliseconds into seconds, or you'll have to know what a microsecond is relative to a millisecond. Okay? Because you need to balance your units. You guys got this in high school chemistry, I'm assuming, right? So let's give an example of this overhead, because I really want to put this home here. So consider a gigabit per second link, which is really 125 megabytes per second, right? Because a byte is 8 bits. And it has a startup cost of a millisecond. This is not unusual for the routers we have today. And if you look, the way we would do that I have two colors here. This is a graph with blue scale on one side and a red scale on the other. Let's look at blue first. What you see here is this millisecond, which is how many microseconds? 1,000. Is an intercept point. So I blow a millisecond with transferring nothing. Right? And then I've got this linear transfer time per, depending on how big I'm trying to transfer my packet. Okay? And if I were to look at the bandwidth that I'm getting, the effective bandwidth, what you see here is that the effective bandwidth starts at 0 because I transferred nothing and it took me a millisecond to transfer nothing, all the way up to the actual 125 or whatever megabytes per second. Okay? And we didn't quite go all the way there. Is everybody with me on that? So you don't get the full bandwidth. And by the way, there is kind of this theorem, which is not even hard enough to even be a theorem, but the point at which I get half of my bandwidth is sort of the point at which the overhead startup cost S times the bandwidth is the same as the size of the packet I'm trying to transfer. So when you balance those two, you get kind of the halfway point. Okay? We'd call that the half power point if this were in another, if this were an EE class, for instance. Okay, questions on that? Yeah?
Decreasing slope of the bandwidth curve is solely because of increasing overhead?
Well, actually, the decreasing slope here is we're asymptoting up to the maximum bandwidth we could get. Think of it this way. What's happening is I'm getting up here, the overhead becomes less and less relevant relative to the transfer time. Whereas down here, boy, it's all overhead and then so as I start transferring some bytes, I start really getting bandwidth out here, and I can't get higher than the bandwidth the link can actually give me. Okay. Now, if you look at a different startup time, like what a disk would have, and I'm not going to claim that a disk can handle a gigabit per second. It's considerably less than that. But if you look, this curve never hits the half power point at all for 500 kilobytes here. If you notice, we basically just barely make it to 35. So that's a quarter of my total possible bandwidth. So this startup time could be an extremely significant part. And this is really, the reason I bring up startup time is really because what do we do in the operating system? We want to get out of the way. Okay, the most important, this class is all about how to get out of the way. Okay, that's another thing to say at parties, right? Because we want the operating system not to interfere, and that overhead is operating system interference in many cases. And so this is where we can tune our device drivers and tune the various aspects to try to get the overhead down so we get higher effective bandwidth for smaller packet sizes. Okay? Questions on that? Now, what determines the peak bandwidth of I/O? Well, clearly the bus speed can make a big difference. And it's been kind of interesting to watch over the years some of the various speeds that have been of buses. So for instance, PCIX was a really big innovation over PCI when it first came out because you could get a gigabit or a gigabyte per second out of it. Ultra-wide SCSI gave me 40 megabytes per second. Things that are serial tend to be even faster. So serial attached SCSI was 1.6 gigabits per second, and USB started out at 1.5. Sorry about the small m there, megabits per second, and the latest USB 3 or whatever is up at 12. So, there's been a constant increase in bandwidth, and why do we want the bus to be as fast as possible? Because it's a bottleneck, and we would prefer the bottleneck to be the I.O. device, which is the thing that's, limited by physics and probably the slow thing. So we never want the bus in the way. So people keep cranking up the bandwidth, okay? And the device transfer bandwidth, like for a disk, and we'll talk about this in a bit, depends on a lot of things, like how fast is the disk spinning, or in the case of SSD, how fast can I read and write the NAND flash? Or how fast is the signaling rate of the network link, so here I'm kind of distinguishing between internal buses, and some might argue a network link is an external bus. You can make that argument if you want. And so, in some sense, what actually determines the peak bandwidth is the bottleneck. And the trick is to try to get the bottlenecks to be as fast as possible so they're not getting in the way. All right. Now, I wanted to do Administrivia a little early today. One of the things I wanted to mention to everybody is that peer evaluations for Project One are not all in from everybody. Please do that if you haven't. We're not going to actually release the final project grades until everybody gets their peer evaluations in. And I wanted to mention about projects. We've had some instances where people are not contributing to the project. I do want to point out that this is kind of a zero-sum game. So if you're not contributing, then your partners are going to be getting some of your points for the project. So ideally, you're all working together. Okay, and this part of the way we evaluate this is by knowing about peer evaluations, but of course, your TAs have a good idea what's going on because they've been talking to you and everything. Okay, but please actually put these evaluations in, and please give us good descriptions of your reasoning behind your evaluations. All right. I hesitate to put a thing up like this, but I do want to say we've had some people come to office hours, why doesn't this work? It's like, well, because it's broken. You should really do some level of debugging. Don't come and say, I have no idea what's wrong. Try to actually come with a test that fails and a description of where you think the problem might be. Okay, because we've had a lot of people come to TA office hours and pile up in front of in front of the door and basically kind of want the TAs to debug their projects for them, and that's not quite the approach. Yeah. Say that again? Yeah, so the AutoGrader can only provide as much feedback as it can provide. I think the key thing is you need to write sophisticated tests yourself. I mean, think of there is a philosophy that we don't say a lot about in this class. Maybe I should say a little bit more about it earlier on, but basically design for test. So when you're writing code, think about how am I going to test this code, not just how do I write it. Well, if it passes your test and doesn't fail the AutoGrader, there's kind of two possibilities. One, the AutoGrader is broken, which occasionally happens, not too often. Or two, you need to write a harder test. I don't know. I mean, it's an interesting experience learning how to do this. But I'm not saying don't ever come in and ask questions. That wasn't my question. But we've had a lot of people, not my point, but we've had a lot of people that have come in and kind of dropped a bunch of broken code on a TA's desk, and that's a problem. There was a question in the back, or? Okay. All right. So don't take this as absolute. It's just kind of something to keep in mind. I really don't know what to tell you about midterm one. It's, we had a couple of questions that ended up taking longer to grade than we thought. But we have a target that it will be out by section tomorrow. So you'll be able to come and talk to your TAs about it. I guess that's good. I was hoping we'd have this on Monday, and it didn't happen. Regrades, since I'll bring this up as well, you're going to have, as soon as we actually release the grades, which hopefully is Thursday, you're going to have a week to submit a regrade request. And I think we'll post on Piazza how to do that, but I believe there may actually be a link in the actual grading program for you to do that. But it should be written justification why you think the grade is wrong. Just be very sure that you actually want this regraded, because when we receive a regrade request, we may actually regrade the whole exam a little more carefully, which might lose you a few points. So we're not saying don't ask for regrades, but just make sure that you know what you want. Yeah. Yep. Part of the reason that it's not graded yet has less to do with the total time between when you took it and now, and the fact that spring break got in the way in places. So, but okay. The last thing I hate to tell you, but if you look on the schedule, we have another midterm, April 22nd. So, yeah, it's coming up. Yes, question.
Will you be getting grades back for that, like, day of the final? Or?
Hopefully so that actually is the second to last week. So our hope is that they will be in either the last week or early part of RRR at latest, but hopefully the following week. The fact that spring break got in the way was a little bit of a problem here. We apologize for that. So, okay. Questions? Yeah. So midterm 2 is about just things from the last midterm to the next midterm, and then the final is about the class. So, okay. All right. So let's talk about storage, unless there's any other administrivia questions. I didn't mean to. And I'm very sorry that we don't have the grades yet. That was not intended. Okay. So let's talk about storage devices. So we have kind of two things that you're likely to encounter a lot of these days: magnetic disks and flash memory. So magnetic disks have the advantage that they rarely become corrupted, although when they do, you lose a lot of data. The capacity, a lot of capacity at a low cost. There's a block level random access, so you can basically read chunks of data at a time and write chunks of data at a time, except for this shingled technique, which I'm going to talk about a little bit later, which is just brand new, which is not quite so flexible. Very slow performance, relatively speaking, for random access, which is something that a file system is going to want to worry about. And much better performance for streaming access. So remember we talked last time about sequential access, such as in reading a video or watching a video as opposed to random database access. The sequential access from a magnetic disk is going to be much faster than random access. Flash memory, which has really taken off over the last decade, is interesting, different technology. Okay, this is actually storing with trapped electrons, storing information. It fairly rarely becomes corrupted, although what's interesting about flash, and I'll talk about this a little bit more, is that the flash memory has got a level of complexity to it that has had some rather famous or infamous firmware bugs that have lost all your data on SSDs. So those of you that have SSDs and think that you're in better shape than having a spinning storage disk ought to make sure that you're backing them up. I got toasted by that a couple of times. The block level random access is very fast as sequential access, so there's no advantage to random versus not random. Performance is good for reads. Writes are slower and actually much higher energy. And you have to erase large blocks before you reuse them, so that's another problem. And they wear out. Okay, so these two types of technology, how many people actually have a laptop with flash in it? SSD? Very significant number of you. How many have a laptop with disk in it? Okay, how many don't have a laptop? None of you. Okay. So it is kind of interesting. You can, if you feel like you like numbers, you can do a Google search about SSD versus hard disk drive and whether we're at an inflection point or not. And back in 2010, there was a huge uptick in this discussion, and people made graphs like this, here's the cost for a unit of SSD versus the typical $50 cost for a disk that might go in a laptop, and look, they're getting close and crossing, and therefore maybe everybody's going to use SSD. And then you get charts like this that sort of compare, look, the access time is faster for SSD, the IOs are higher per unit time, there's a lower failure rate, the wattage, power use is lower, only 1% of the CPU is used up, there's 20 millisecond access time versus much higher for disk, and backups only take 6 hours versus 24 hours. And you very easily could say, well, that clearly says that SSD is better than disk on all metrics, except the one that's missing up there is what? Cost, and then also size. Okay, so spinning storage still has a non-trivial advantage on size. Okay. So let's start with, was there a question? No. Let's start with hard disk drive. So hard disk drives are one of those things that, as far as I'm concerned, are magic. Okay, the density that's on these platters now, so there's a bunch of spinning platters that are magnetic on both sides, and the density of bits is at 1 terabit per square inch. Okay, so imagine a square inch and imagine a terabit in that square inch. That's pretty impressive. The heads themselves are actually, these GMR heads are as complicated to fabricate as chips. In fact, a lot of the chip fabrication process is used for them. And we'll talk more about this, but essentially the platters are spinning, the heads go in as a group and out, and there's a head on both sides of the platter, and that's what happens when you read and write data. Okay? I put these up here because I think these are pretty cool. Back around, what am I going to say, 2000 or 2001, whatever, these actually were better than Flash from a density standpoint. This is a 1 gigabyte, so you can imagine this is a long time ago. Storage device that fits into cameras that's actually spinning storage. There's a little platter inside of there that spins. Okay, and it's small enough, it's the same size as some of the bigger Flash chips, and it would fit into your camera. So that's kind of cool. Anybody ever seen one of those? Yeah. I actually still have one at home somewhere in a camera that's thrown in a corner because I've got a much larger camera now and a much larger storage. But so what do we know about disks? So the unit of transfer on a disk is a sector. So this is why we call it a block device. And a sector is one of those little pie-shaped chunks there. Okay? Does anybody know how big a sector is typically? 512 bytes. Good. You remember that. I told you that earlier. Now, the new ones are they're actually disks you can buy that have 4K sectors on them. But that's a relatively new thing. If you take what you call a track is kind of the circular ring you get by leaving the heads alone and letting it spin all the way around, that's a track. If you take all of the tracks that are on top of each other, that's a cylinder. So basically, when you move the head in, you read and write a whole cylinder, and then you move to get to a different cylinder. Okay? Disk tracks are about a micron wide or so. Okay, a micron is 10 to the minus 6 meters, right? The wavelength of light being 0.5 microns tells you a little bit something about how close the tracks are to each other. Okay, that's 2 wavelengths of light. And the human eye can see 50. Okay, so there you go. We get about 100K tracks on a typical 2.5-inch disc. So these are the smaller ones that go into smaller laptops. There's guard regions around the outside to avoid corruption. Typically, the other thing to notice is the track length changes depending on where the head is. Everybody see that? Right? When the heads are on the outside, the track is longer. When the heads are on the inside, the track is shorter. Okay? Everybody's got that, right? 2 pi r. You remember that one, right? And the thing that's interesting about that is there was a big change in the 90s that happened with disk drives where originally what happened is if you imagine a slice of pie, okay, and because it's April Fool's, we're not talking about the number, we're talking about coconut cream. You could imagine that the sectors actually were bigger on the outside than on the inside because there was a chunk of things were split up as a chunk of pie, and so that meant that if the spindle was going at a constant rate, then this disk head got bits off and on at exactly the same rate, no matter whether it was on the inside or the outside. Okay, that was much easier electronics, but it wastes a lot of density on the outside, and so by now what happens is the bit rate speeds up when you're on the outside and slows down on the inside. And they use DSP chips to work that out. Okay, and by doing that, the density per square inch is the same on all parts of the platter. Okay, so the original case, the density was less on the outside than the inside. Now it's the same across the board. All right. The last thing I wanted to mention, since this is relatively recent, the last couple of years, is this thing called shingled magnetic recording. And here, they actually overlap tracks. Okay, so one track, you write a track, and then you write the next track, and it's like shingles on a roof. It sort of overlaps the previous one. And you can actually get, many more tracks as a result, but you've got to use a lot of DSP to separate those apart when you're using them. And more importantly, when you go to try to rewrite a track, you now have screwed up the previous track, and so you actually have to write groups of tracks at a time. Okay, so SMR gives you high density. Like, for instance, Seagate's got an 8 terabyte drive they announced, and Hitachi a 10 terabyte drive they announced last November. Can you, by the way, that's 8 terabytes, 10 terabytes. Those are big. Yes, question?
So, is there a lot of extra overhead introduced with these shingled magnetic?
Well, so this is clearly an overhead density trade-off. All right? So these particular drives are great in the very large storage server applications. You could imagine if the only thing you ever stored was huge videos, this would be great, right? Because you just basically pull the videos off. I can't wait to have one of these in my TiVo, I'll tell you that much. But yeah, so not only does it introduce overhead, but more importantly, it's kind of funny. If you guys look these drives up, you'll see, well, Hitachi hasn't released theirs for a while because there's some concern about whether the software will be up to working properly, so it doesn't work on personal computers. It only works on Linux servers so far, but they're hoping pretty soon that the software will do this. So these are harder to use, but they're much denser. Okay, question, yeah?
Does the motor usually spin at the same rate?
Yes, motor spins at the same rate.
So does that mean that the outer tracks are faster than the inner tracks?
The outer tracks, the rate at which the outer tracks go under the head is faster, yes, which means that the bit rate of the bits coming off gets faster on the outside than on the inside. Okay, and by the way, people building file systems take advantage of that. They put things that you want to access really quickly on the outside, but it's a little bit of a difference. Yeah, go ahead.
So I know there's like different RPMs for these things. I know there's like a physical consideration. Like when you're spinning that fast, like is it less durable or do you have like lower lifetime?
So that's a good question. So, and I'll say more about this in a moment, but there's two issues with spinning. One is the faster you spin, actually, there's an advantage to spinning really rapidly in that you get very high bit rates. That's good. Okay? The downside of spinning really rapidly is, one, you're using up a huge amount of energy to start and stop the drive, among other things, but also there's a huge amount of resistance from the little air that happens to be inside of these things. And by the way, these heads are flying basically, half a micron or something above the surface. And so there is a lot of interference with high speed and what's in there. So Hitachi, I wasn't going to say a lot about this, but Hitachi uses helium inside of their drives instead of regular air as a way of getting the density down and making the resistance less. So speed can matter that way. And so you never see faster than like 7,200 RPM in laptops because it just burns through energy too fast. I mean, your battery would go south. Okay. So cylinder, I already said, is all the tracks under the head. Read-write is a 3-stage process. So the seek time, you move the head in to where you want it. And then you rotate, you wait until the sector you want is under the head, and then finally you read it off at whatever rate that is. So if we were probabilistically characterizing the rotational latency, how much of a turn do I have to, on average, go through to get to the sector I want? What was that? Half. Yep, half of a turn. Has everybody got that? I move the head in, I'm in some random part of the track, and so I wait for, on average, half of the spinning time, and I get the data I want. All right. So we can actually put together a little formula here. Queuing time for disk latency. Queuing time plus controller time plus seek time plus rotational time plus transfer time. Those bottom 3 are the physical ones, right? You move the head in, that's seek time. You wait till it rotates for where you want, and then you transfer. The controller time is very dependent on what hardware you're using. Is this a SATA disk, a SCSI disk, what have you? And queuing time is interesting enough that we're actually going to talk about that in a bit. Okay? Questions? So this is a very simple mechanical model. And what's the highest bandwidth off of a disk? Park the heads, read a whole track. That's really high bandwidth. Okay? Because you're not waiting to move things in. You're not waiting for the rotational velocity to happen. Yeah, question?
Read from multiple tracks in the same cylinder?
That's a really good question. Can you read from multiple tracks in the same cylinder? Usually no. Even though the heads are all there, the problem is that the amount of CPU processing time required to disambiguate things coming off the disk is usually so much that a commodity drive, you only read off of one surface at a time. And by the way, the answer I just gave you is exactly the same reason you don't have independent heads as well. Okay, you park them all together, you move it in, you pick which platter you want to read off of, and so on. Good question. Yeah.
How does the disk know which part of the track?
How does the disk know which part of the track? That's great. So every sector has, in addition to, say, 512 bytes of data, actually has a header on it. And so what's happening is this thing is spinning around, and the controller is waiting for that header to say what's the right sector, at which point you just grab it, the data. Good question. Any other questions? So some typical numbers for disks. I wanted to show you this. So space is, we're getting up to 8 terabytes and 10 terabytes, although these are kind of esoteric. 6 terabytes is more standard technology these days. Areal densities are like a terabit per square inch, which is over the top. Seagate has been resisting helium. Several other folks have been using helium, so we're really kind of dealing with the turbulence inside the actual disk drive itself. Is things that people are starting to optimize for. Average seek time is somewhere in the 5 to 10 millisecond range. I've seen them as low as 3, I guess. I will mention that when they spec this time, you actually go to Seagate's website and you say, what's the seek time? And they say 3.5 milliseconds or 5 milliseconds. That's assuming you go randomly from any track to any other track. So they basically add up all those times and divide by the number of experiments. In reality, a good file system will have a lot more locality, so the time to seek to the track you want is going to be much shorter than that time. Okay, often close to a third or 25%. The average rotational latency, typically for laptops and desktops, somewhere in the 3,600 to 7,200 RPM, which is somewhere between 6 and 8 milliseconds per rotation. Server disks can be as high as 15,000 RPM, so there's a big difference. These guys are burning a lot of power just to spin up. All right. Controller time depends a lot on how it's connected. Transfer time, you can get 50 to 100 megabits or megabytes per second. I've actually seen 200 or 300 in some extreme cases. The transfer sizes are kind of in the 512 bytes, and I've even seen 4 kilobytes. I should update that number. And that transfer time depends on how fast is it spinning, how big is your sector, how long does it take the head to go underneath, right? You can imagine that. You got to wait for the bits to go down before you go under your head. And the cost seems to drop by a factor of 2 every 1.5 years for the same size. So, kind of run it. You know, what's funny, to the extent that this trend is not continuing, it's because the industry had decided that people didn't need drives this large. Okay, once you start getting into the 8 and 10 terabytes, the biggest problem with that is, nobody with a laptop's going to need that really. And in server farms, the problem with something that big is to back it up, it's going to take weeks, and so it's actually, there's a limit of how big things can get just from a utility standpoint. Now, I would say things like DVRs that are storing huge amount of video is probably a pretty good example of something that this might work on. And in the server space, you use RAID, which lots of copies of stuff, and then it's okay if it dies. But, yeah. So it's not a technology limit in the case that it's not doing that. So let's just give you a really quick example. So let's ignore queuing and controlling the controller times. We have an average seek time of 5 milliseconds. Let's suppose we have a 7,200 RPM disk. What does RPM stand for? Revolutions per minute. Yep, or rotations per minute, okay. So to figure out how long a rotation takes, units, right? 60,000 milliseconds per minute. Everybody got that? Right? Because there's 60 seconds in a minute and 1,000 milliseconds in a second. All right? Over 7,200 revolutions per minute. The M's cancel, and you end up with milliseconds per revolution. I didn't write it there, but it's about 8 milliseconds. Okay? Everybody with me? Now, transfer rate, if you got 4 megabytes per second, let's say, sector size of a kilobyte, you can actually do that computation and come out with about 0.26 milliseconds to transfer a sector. And notice to be perverse here, because it's April 1st, I decided to really make this all the way out here. So the size of the sector of 1 kilobyte is 1,024 bytes, but the transfer of 4 megabytes per second is in 10 to the 6th increments, and so I divided that out that way. Just because I can. If you're never quite sure which types of units are being used when they say K or M's, ask. Okay? So if we want to look at the time to read a sector from a random place on the disk, we add up the seek time of 5 milliseconds, half of a rotation, 4 milliseconds, transfer time, 0.26. That adds up to not quite 10 milliseconds, and so we can do about 100 kilobytes per second that way if we keep reading randomly. If we don't change the heads, but rather just read from random sectors on a track, which really doesn't make a lot of sense, but it's illustrating a point here, that kind of doubles to about 200 kilobytes per second. And on the other hand, if we just read the next sector on the same track, it's about 4 megabytes per second. So there's a strong advantage to going for locality on a disk. And most of the file systems we're going to talk about are all about locality, because it's so important not to move the heads. All right? Everybody with me on that? Okay. Questions? Don't you love units? How many people remember matching your units up from chemistry? Everybody remember that? Or physics or something? That was one of the most eye-opening experiences I remember. Actually, maybe not. Go ahead. It's very important, though. How can you use locality when you don't know what the data access pattern is? Well, that's a good question. The answer is you can't. So the way you get locality is you have to have some notion of how people are going to use it. And what's great about big files that maybe are used sequentially is you know how they're going to use it, and so you want to wrap a big file on the same track and then tracks that are close to each other, right? There's a good example of, looking at how a user uses some data and mapping that into how I get locality out of the disk. Okay? Good question. Yeah.
So the file system is aware of which track the sector is on?
So that's a great question. The file system's aware of which track things are on. So not anymore, but there is a virtual kind of block ID that the file system is aware of, where you start numbering the good blocks in a certain order. And things that are close to each other are roughly on the same track. And so it's locality within that namespace, but it doesn't actually know what track you're on anymore because the disk controllers don't let you know that. I'll say more about that in just a little bit. If you actually look at the old BIOSes for PCATs and some of those old computers, they did actually know about what track and sector and so on you were on. But that hasn't been true for quite a while. It's a good question, though. So just that you bring that up, lots of intelligence in the disk controllers now. So sectors contain very sophisticated error-correcting codes. Reed-Solomon is the type of code. The disk head basically writes over more than just a single track, even without the SMR, and so there are some errors that get introduced whenever you write, but there's also corruptions for lots of other reasons, just random noise in the system, and so we need error correction code. So when you read data off of a disk, it's often got errors in it, but that's okay because it's not that you put down 512 bytes worth of data. You put enough extra on there that you can correct for it. Okay. And things like sector sparing are done by the controller, so the controller knows which sectors are bad during a formatting process and hides that from even the operating system. Okay. Slip sparring, so you remap sectors to give you sequential behavior so that the operating system's making some guesses and things basically stay sequential. And then skewing tracks. There's a lot of optimizations that the controller itself does. And operating systems think that they have a good notion of what's going on in a disk, and they do some optimizations, and that doesn't always map what's really on the disk. So there is a little bit of a conflict there in modern systems. Question? Oh, no. Okay. So flips. Yeah, go ahead. Yep. Yes. Well, it happens. It varies a lot. Too much for me to pull numbers out of my head here as to what any given drive is, but it does happen a lot more than you might think. But there's a lot of redundancy that's put in there. It's not twice, but it's 10, 20% bits are redundant on there. And I don't know what the rate is that errors happen, but it has to be low enough that error correction can meet the really low error rate of the actual data bits you care about. So it doesn't happen that frequently, but it happens much more frequently than you might think.
So it's not like once per 2 days?
It might actually, you know what, I don't know if I've done that calculation. I tell you what, I'll bring it next time. That's a good question. How often per day is it, or anyway? I think that depends also on how much you use it, obviously. But let's talk about SSDs. So these guys have come through a tremendous change over the last couple of years. So in 95, people started replacing magnetic media with non-volatile memory, which actually meant there were special chips you could buy that were regular DRAM chips with a battery on them. Can anybody guess why this was a useful technology? Yeah. Yeah, that's a great example. So on RAID cards, so that your writes would be preserved until they got to the disk. The continuation of that is basically the committing of the log in a database. You can commit to the DRAM, the non-volatile DRAM quickly, and even if the power died, you're good. But it's similar to what you just said, yes. By 2009, so then then RAM slowly came into play, and by about 2009, there were lots of multi-cell RAM flash RAM types of things where each cell actually was 2 or 3 bits per cell of flash. And this is kind of interesting because you use trapped electrons to tell you what value is stored in a cell. And so what that means is, for instance, in the 3-bit cells, that's an MLC, multi-level cells, you actually have 8 different levels of charge that can be tracked in order to get 3 bits. Okay. Sectors tend to be about 4K, and however, they're stored in memory blocks, and I'll show you that in a moment. And the basic technology here is trapping electrons. There are no moving parts, so that's a great thing. Nothing to fail. So there's also no seek and rotational delay. Basically, a block is a block. You can grab it when you want it. So there's no advantage to random versus sequential in a NAND flash. So if you think about that, imagine all of this OS technology built up over the years to deal with the fact that you're trying to get locality out of a disk drive. Suddenly that stuff doesn't matter when there's a NAND flash involved. All right? And the operating systems have been a little bit slower than you might expect to go for special versions of file systems based on the fact that there's only solid-state disks there. The other thing that's very important about flash is that they wear out. So a good number is something like 10 to the 6th writes, and then suddenly you no longer have as many bits as you thought you did. Okay, so what happens in the multi-level cell technology is these trapped electrons get trapped in a way that they don't come out when you try to erase, and as a result, you start with 3 bits, and then you go down to 2 bits per cell, and then 1 bit per cell, and then no bits per cell. Okay, and so your storage capacity in a given cell starts shrinking. And the way people get around that is they make sure to do what's called wear leveling, which is when you're doing writes, you try to spread all the writes out over the cells so they all wear out equally. Okay, and that actually means that in the background of file systems, the operating system's doing one thing. The NAND flash is busy moving data around and making decisions about where to place data to do wear leveling. And it's that technology that's moving data around to do wear leveling which bit me at least twice over the last 5 years, where I had a complete failure of an SSD in one of my laptops because the firmware had a bug in it. Okay, so SSDs are getting a lot more reliable, but you got to be careful which ones you got. Okay, questions? Now, capacity keeps going up, right? So you can easily get 512 terabyte SSDs now, no problem, right? I have a 512 in my laptop, not a big deal anymore. Okay. So let me just show you briefly the architecture of an SSD. So the NAND flash typically has many cells in a block, all right, and there's a memory controller that controls all this and provides a virtualized notion of block IDs to the host. And so the host is reading and writing NAND, but in fact the physical cells it's reading and writing have nothing to do with the ones it thinks it's writing, because there's a virtualization layer there, and that's to allow this memory controller to move data around to do wear leveling. Question, yes? Yeah, they're like a simplified, they are a processor. Yeah, they have firmware. There's a new trend in the higher end systems to start looking at just having flash without the controllers that are like DIMMs that go into the high end servers, and then your operating system has to do the wear leveling. That's, then it's not called an SSD anymore because it's not at the interface of a drive. It's actually just RAM. That's a new trend, but it's not that prevalent. So basically, the interesting thing about this is now our latency is really just queuing time plus controller time plus transfer time. There's no longer any of this move the head in, wait for the rotational latency. And the highest bandwidth here is sequential or random. Okay. There is one other interesting thing, however, which I wanted to briefly mention, and that is 4K block for reading and writing, but the 4K pages for reading and writing, but they're in blocks which are much bigger, like 256 kilobytes or larger. And the thing is that you have to erase the whole block at once, but then you can write and read individual 4K pages. So the way a file system has to use this is that it has to have a bunch of completely erased blocks that are on a free list somewhere, and then you can read and write pages. But before you can overwrite them again and reuse them, you have to erase the whole block. So you can imagine the management's a little more complicated here. Okay? And that just has to do with the way they're set up. And erasing of blocks takes time. Writing is much slower than reading. Erasing is much slower than that. And this, by the way, this range here is because this is including erasing. So the rule of thumb on NAND flash is that writes take about 10x the time of a read and erases another 10x of write. So really doing erasing of a block is something you want to do in the background, never on demand. Sounds a little bit like what we said when we said there was a free list attached to a clock algorithm, right? It's the same kind of idea. Question, yeah? So the difference is that you can only add electrons, you can only trap more electrons in the writing process. The erasure process deletes all the electrons and gets them out of the channel, and then you can add electrons again. You can't remove them with the write process. That's a good question. And actually, yeah, go ahead.
Is this the erasure process what we call trim in the SD?
Yeah, it is partially what is involved in trim, yes. Okay, so since it's April Fool's, I thought I'd give you a calculation, which again is not a joke, but it's amusing. So is a full Kindle, which has SSD, which has flash memory in it, heavier than an empty one? How many people think the answer is yes? How many people think the answer is no? How many people think it depends a huge amount on circumstance? Okay, the latter of you are kind of correct here, and I'll tell you why in a moment. But yes, you can actually say yes, but it's not by much. And the reason is, I mentioned this briefly, flash works by trapping electrons. So the erased state is lower energy than the written state. Okay, because you get rid of all the electrons, there's nothing trapped, but as you trap them, they're in a higher state and therefore more energy. And as a result, we can use E equals mc squared, believe it or not, because that's about energy, to come up with the effective mass and therefore weight of this. And you could compute what the trapping is. It's about 10 to the minus 15 joules and you say, well, in a 4 gigabyte flash, about half of the bits are 1 and half are 0 if it's full. Okay? And how much do you think this calculates to? An attogram, 10 to the minus 18th gram, which is, of course, much smaller than the most sensitive scale out there, which is 10 to the minus 9th gram. So, yes, it's heavier, but you couldn't possibly measure it, so don't worry about the weight it's going to add to your backpack. Now, the question would be, what's missing in this calculation? Yeah, go ahead. Yes, so the battery is a lot lower energy. So the thing is a lot lighter than 10 to the minus 18 right after you filled it up. Okay, because the battery energy is way lower than what you just put in here. Okay, and the reason for that is there's a lot of heat generated and all that sort of stuff going on. So not only is the battery's lower energy, the Kindle is warmer, so therefore it's a little heavier. Who knows what comes out of this, right? So this experiment is 100% only about the flash memory, ignoring anything to do with thermal energy or anything to do with the battery. And so the way you'd have to do this experiment for real is you'd have to actually take the Kindle, cool it to a well-defined temperature, charge it all up, then fill it with books, go back, charge it up, cool it down, weigh the difference, which of course you can't do because there's not a scale that's sensitive enough, but if you did that, you would find 10 to the minus 18th grams heavier. Now, the reason I mention this, by the way, is there is actually an article in the New York Times with this calculation. I got contacted back in 2011 by some science writer that said, we like to answer questions, and somebody asked this question, is a Kindle heavier? And so I gave him this calculation. The thing that's you should look it up. I'm not making this up. But the funny thing about it, this is a perfectly okay calculation, but it's so amazingly qualified, right? I mean, there's so many buts on this, right? Subsequently, we had absolutely crazy folks tell, there were videos saying how the internet was the weight of a strawberry, and they were just doing all of these bizarre calculations that made absolutely no sense. So this is what I get for having a fun answer to a question in the New York Times. Anyway, all right. Back to this. So if you actually look at the difference between performance and price, the really biggest thing here is, this is in January of 2013, the biggest thing is the difference between the sizes. There's a non-trivial size difference. DRAM is really small but really high bandwidth. Disk is low bandwidth but much bigger, and this of course is 6 and 8 terabytes now. And SSD is somewhere in the middle. So it's up to you as to where you think it belongs. I actually think SSD makes perfect sense in a laptop, assuming you back it up. And disks make perfect sense in pretty much anything else where you want really high storage, like in a server farm or something. Okay? Great. So the summary on this, low latency, high throughput SSD advantages, no moving parts, read at memory speed. Cons are relatively small storage, asymmetric writes, and limited lifetime. And so if you really want something interesting, what Seagate and a bunch of other companies have done recently is they combined flash on top of spinning storage, and now you've got a fast cache with flash and the density of spinning storage, and by the way, that's a cache for storage, right? Okay. So what goes into the startup cost for I/O? System call overhead, operating system processing, controller overhead, device startup, and queuing, which is our next topic. But we're going to take a break. You guys can contemplate how heavy those Kindles are, and we'll see you in a moment.
Yeah, S-E-A-G-A-T-E, just like it sounds. S-E-A-G-A-T-E. Seagate. Sure. All right.
Let's continue. So we've been looking at I.O. performance here, and we've been talking about the devices. We've been kind of not talking about controller because that's a piece of hardware that pretty much is out of our control, no pun intended. We have not said much about queuing time, and so there's a lot of metrics we could come up with, like response time, throughput, etc., and we did talk about effective bandwidth earlier. But what are some contributing factors to the overhead and the latency? Well, certainly software paths through the operating system are a key contributor of overhead, and that can loosely be modeled as a queue with some qualifications. The hardware controller and I.O. device time, those are hardware elements. Okay, so we're now going to talk about, can we even talk about the software component? And that's going to be this green element. And the thing about queuing behavior, which people don't realize until somebody mentions it to them, is it can lead to huge increases in latency that have absolutely nothing to do with the service time of the device and have a lot to do with the randomness of the arrival time of the requests. Okay? So, in fact, I mentioned this earlier, but if you were to take a throughput here, or throughput versus utilization graph, or a response time versus utilization graph, you'd see something like this, which starts out kind of reasonable and linear, and then rapidly kind of goes through the roof as you get close to 100% utilization, and that's the queuing behavior. Okay? Now, if we had a simple deterministic world, this would be great. What's a deterministic world? It's a deterministic world is one in which the time for arrival is exactly the same for every item. There's TQ is the time in the queue. The service time, T sub S, is there. And in that perfectly linear world, we can say exactly how long it will take from when we arrive to when we get out. It's going to be TQ plus TS. And the reason for that is we're not overloading the system. We know that we'll be the only person in the queue when we arrive. We'll get serviced right away. And this seems great. Okay, and of course the world's not like this, but this is assuming requests arrive at a regular interval, take a fixed time to process, and there's plenty of time in between. And if that were the case, we can talk about some fairly simple ideas here, like how fast am I servicing things? Well, the service rate at which the server can work is 1 over the service time. Okay? The arrival rate is 1 over TA, arrival rate. So these are two rates that we can talk about. Now notice that the throughput of this, what is the throughput of this? How fast are things coming out of the departure lane? Can anybody figure that out? What? Well, the service rate is as soon as the person gets to the counter, how long does it take to serve them? That's a little different than how fast are people coming out, right? Well, there's only one other number here, right? So the arrival rate, arrival equals departure. There's another chemistry. We're doing chemistry today, right? Remember detailed balance, right? The rate of the molecules in equals the rate of the one out. What if that weren't true? What if arrivals were faster than departures? What happens? The queue would fill up, the queue would blow up, the whole system, no, whatever. I mean, the queue would fill up if arrivals are faster than departures, right? So that's clearly a mode which we better not be in, one in which the arrivals are faster than the departures, because we want to have the steady state scenario here. And so the utilization, which is another number we can talk about, is lambda over mu, and lambda better be less than mu. So this number, u, shouldn't get bigger than 1. That's the utilization. Okay? Now, and the average rate is the whole story here. So in an ideal linear load, if we look at the offered load, which is how fast things are arriving versus what the throughput is, you can see that we've got queuing delay is fixed, and assuming that we don't have utilization greater than 1, we're good to go. So we just keep adding more and more people as we go faster and faster until lambda over mu hits 1, and then what happens? Well, now we saturate. Okay, so now our little nice linear world is no longer so good. Because what happens to the queue when we're greater than 1 there? Yeah. So here's a situation where the delay of the person sitting in the queue depends on when they arrive. So suppose we're talking about coffee just before class because, you want to stay awake during Kubatawas' class, right? So this is 4:59. Everybody shows up. The time you wait depends a huge amount on when you arrive, because if you're in this early stage where the queue is short, you get serviced quickly. But if you're there after it saturates, then depending on how long you wait, you end up with more and more and more time. Okay? So this is a bad queuing effect. But it's not quite as bad as what we think about. But if you look at what the queue wait time looks like, it's growing unbounded at a rate of TS over TA until the request rate subsides. So basically that's at 5:10, when you're all sitting here waiting for class, then the rate starts subsiding. Okay, and all of these poor people that wander in late because their coffee, they got to the queue too late. That's too bad. So, questions? So what would make the real world not linear? So multiprocessing would change slopes in here. That would help us. But what might make this not so nice? Burst. Who said burst? Somebody, good. Bursts make this not nice, right? Because what I'm assuming here, if you look at this is a really idealized scenario, because we always arrive, we pick our arrival rate and everything arrives at that rate. Okay, the real world's not like that, right? Because at 4:53, there's nobody in line, and at 4:59, all of you are in line, right? Because you need coffee before this class. So, the real world is bursty. And so if we look at a bursty world, what we see here is a request arrive in a burst, and suddenly you've got the first one arrives, and the server starts working on them right away, but the next one arrives, and they sit in the queue. And the next one arrives, and they sit in the queue, and so on. At some point, the blue one gets their coffee, and now the white one takes over, and the queue length gets a little shorter. The orange one takes over, the queue length gets a little shorter. Finally, the blue one gets their coffee, and we're good to go. And what you see here is, even though the average arrival rate might be the same as in the previous diagram, we have these bursts where the queue grows. Okay? And the output is also a little bit bursty, because what you see here is there's coffee, 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 nothing, and then coffee, 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 coffee. So there's bursts. The bursts on the input end up as bursts on the output, but they smooth out a little bit based on what your server's like. Okay, and so the real problem with queues is bursts. Okay, and so then the question is, how do we characterize bursts? Well, it seems complicated, right? There's lots of ways you could characterize bursts. An interesting one, which I like to talk about, is the so-called memoryless distribution, which is exponential. You can write it like this, f of x equals lambda e to the minus lambda x, and it's called memoryless, and it looks like this. And the reason it's called memoryless, and this is basically the distribution that says what's the chance that a burst, the time between an arrival is 2 or 1 or 0. As we get at the low end here, the probability goes way up of a short time between arrivals, but there's always some very long time between arrivals. This is sort of during class, none of you would think of leaving to go get coffee, so there's obviously a long tail there, right? So why is this called memoryless? Well, the mean arrival time here, 1 over lambda, is a nice number. The reason this is called memoryless, anybody want to guess? I mean, I say it here in blue, but what does that actually mean?
Is this like a signal processing concept?
Well, they use it in signal processing all the time. It's a property of this curve. And the property of this curve is, if I know that I've waited for a second, and I say, well, given that I've waited for a second, how long am I going to wait? Right? That's a conditional probability. The curve looks exactly the same. So if I know I've waited a second, that tells me absolutely nothing about how long I wait. Sounds like a Berkeley bus, right? Okay? So that, and this is a great distribution, not because it's a perfect indicator of the way the real world is, but because a lot of things where you have a lot of events together and you look at them in aggregate look like a memoryless distribution. So if you take a bunch of atoms that are all decaying, individually they have this really weird probability distribution, but if you take all of them together and look at the radiation coming out, it tends to be memoryless. And so this is, and what I just said there, by the way, if you say that in a math class, they'll say, ooh, obviously some idiot professor told you that. That means nothing, right? But it's roughly true, okay? It kind of converges that way a little bit. And so in this distribution, there's lots of short arrival intervals and a few long gaps. And the reason I mention memoryless is, A, it's not a bad model when you don't have enough information to know better. Let me say that again. It's not a bad model when you have a lot of events and you don't have enough information to have more information. And the second thing about it is it's one of the few cases where we can talk about queuing theory easily. Okay, and so let's assume that we're talking about an arrival time that's exponential, or memoryless. And so then we can talk about the server. How long does the disk take? Okay. Now, how many people have taken some probability? You've all taken probability, right? Do they teach that in one of their classes, low-level classes? So the key thing is the server spends a variable time with the customers, and we can talk about this distribution like this, which is there's some mean and some distribution, and so the probability that the server takes some amount of time here is the area under the curve. Okay, and this is just like you go to McDonald's, and you're waiting, and sometimes it takes a really long time, sometimes it doesn't, right? It may vary depending on what you ask them for. Do you get that hamburger, or do you get that healthy salad? Clearly the salad takes a lot longer for them to put together, usually. Probably for other reasons than we might think. But you can come up with the mean, variance, which the square root of is a standard deviation. I'm not going to go in these, but these are all terms that you've heard about. The standard deviation is kind of a measure of how the spread, right? You guys are aware of this from tests, right? The one I wanted to point out to you, though, which is interesting, is C. This is the new one. C is the variance squared, the variance basically over the mean squared. This number, it turns out, is unitless. And for a memoryless distribution, C is 1. Okay? For distributions that tend to have really long tails, C is bigger than 1 because there's a huge variance. And for things that have much shorter tails and tend to be more deterministic, C is closer to 0. So if it took exactly the same amount of time all the time, C is 0. Memoryless is 1. Long tail is bigger than 1. Okay? And it turns out, if you're willing to grant me that, then we can actually do something interesting with C. Okay, for instance, disk response times are often shown to be a C equal 1.5. Okay, that's just because they're very long tail. There are short seeks, but there tend to be really long ones as well. Okay, good. Now you can come back because we can say, look, what is the queuing time through here? We can talk about the whole system. We can talk about the arrivals and the departures. We've already done that. And the arrivals are characterized by some probabilistic distribution. We're going to say memoryless. The departures are characterized by something else, which can be variable. And we can actually measure something here, okay? And before I do that, I want to tell you the Little's law, right? How many people have heard of Little's law before? Okay, what is Little's law? Little's law says basically that in any stable system, so we're not talking about bursts right now, we're talking about stable averages, the average arrival rate is equal to the average departure rate. So that means that as arrivals come in, there's a certain rate they come in, and there's a certain rate they go out. Didn't we just say that? Right? Otherwise, the queue wouldn't be stable. And the reason I call this the McDonald's law is what this really says is you come to the door and there's a line in front of you, and you count the number of people, and when you get to the counter, you turn around and you look. Okay? And the question is, how many people are behind me in a stable situation as were in front of me when I came in the door? The same. Right? And so Little's law basically says that if I take the total number in here and I multiply the time I waited to get in there, which is 1 over b, I can find out what L is because it's basically related, the number of people in front of me and the number behind. Okay, and so we can write this as sort of N equals B times L. And it turns out from this is regardless of bursts or anything, and from that you can derive all sorts of queuing theory. Now I'm not going to derive it for you, but I'm going to give you some results which are useful. So here's some assumptions. System is in equilibrium, so the queue is neither growing nor shrinking. Very important. The time between arrivals is random and memoryless. So notice we have memoryless input. The service rate, the server can have any sort of complicated service behavior, okay, but it has a service time on average T service, and mu is 1 over that, which I showed you earlier. And so here are all the parameters we can talk about, and they're going to talk about this in section next week. But lambda is the average arrival rate in a memoryless system. T service is the average disk service time. C is that magic C I told you earlier, where if it's 1, we've got memoryless. If it's 0, we've got deterministic. If it's something else, it's something else. And the utilization here is basically lambda over mu, like I said, or lambda times T ser. So this are just a bunch of parameters. I would say if you can get a handle on these parameters and understand where they come from, the red ones are your inputs, the green ones are derived, you can do this. You can say, how long did I spend in that queue? What's the length of the queue? Well, if I know how long I spent, I can just multiply by lambda. I've got the length by Little's law. And so here, pop, are the two results that matter. So if the output is memoryless, look, I take the time that the server takes on average times utilization over 1 minus utilization. What does that curve do as u goes to 1? Goes to infinity, right? That particular, I've even, I'm not going to do it this term, but I've even derived that equation in class in past terms, and it's really easy to show, and I'll put up on the handouts page, you can see how it's derived. But there you go, is a very simple model that's easy to derive that has that behavior of going to infinity as you get to 100%. And by the way, the only thing you need when C is not 1 is the bottom equation. Okay, so you can characterize all sorts of stuff. If a disk drive happens to have a C of 1.5, just use the bottom one. They all have u over 1 minus u. Okay? So, for instance, very quickly, you could do this. What are some usage statistics? Well, we can have 10 requests per second. The requests are exponentially distributed, and the service is exponentially distributed. The average request time is 20 milliseconds. And so now we can ask questions. How utilized is the disk controller? Well, it's lambda times T ser. So look, lambda is 10 per second. T ser, average time to service the customer, is 20 milliseconds, which is, by the way, 0.02 seconds. Utilization is lambda times that, 0.2. So are we making this disk too busy? No. We can add, the average time in the queue is that equation I showed you, T ser times u over 1 minus u, 5 milliseconds in the queue. Okay, how long, so that's basically, I just computed how long you're in the queue. And the question I have for you is, if I want to say how long does it take to get my disk request serviced from the moment I enter the queue until I'm done, what do I got to do? Time in queue plus service time, right? Okay, so I can figure out how long the queue is. The total time in the queue plus the service time is 25 milliseconds because I took 5 milliseconds waited in the queue and another 20 to get my service. There you go. Okay, this is a very simple, it looks a little messy now, but this particular queuing equation you can play with in a wide variety of tasks to see whether you're getting too close to a utilization of 1 or not. It's a very simple equation. It looks messy, but get those pieces figured out and you should be good. Okay? Question? Obviously, there's all sorts of assumptions on this. You got a memoryless input, There's no assumptions on the output. Basically, any distribution works on the output. You just have to compute C. That's a kind of a cool thing about this. Okay? So there's some stuff on the handouts page which I'll put up there. It's some old midterm twos if you want to kind of see what I did are off of my homepage. So how do we improve performance? All sorts of things. We can make everything faster, put some parallelism in, optimize bottlenecks, do other useful work while waiting. Yeah, question.
Is the parallelism not necessarily true because paddock cables are slower than static cables?
Well, that's an interesting question. Parallelism sometimes gives you performance improvement. Okay. Cues are there to absorb the burst and smooth the flow, but if you get close to 100%, you got trouble. Okay, so that's the thing you should keep in mind. Never, what does Kubatowicz say? Never run anything at 100% ever. Okay? Now, by the way, one last thing. I was supposed to talk about a little more on file systems today. I'm afraid I'm not going to make it there, but I did want to say the following. Why does this curve go through the roof? Well, yes, because eventually you're going to be waiting forever. That's correct. What else? Why did my deterministic example I started with the coffee not go through the roof at 100%? It was perfectly okay. What was different? This is bursty. The first one wasn't, right? So the difference here is the memoryless input. That's what causes this behavior. If I have deterministic input, if every student arrives at the coffee house at exactly the same rate, always, you don't get this. But when you design your next system, are you going to trust that it's 100% deterministic and therefore run it at 100%? The answer, Kubi, is no. Okay, good. And once you start putting finite cues in here, this gets pretty interesting. Okay, so when's disk performance highest? When there's big sequential reads or when there's so much work to do that they can be piggybacked. I can show you that in a little bit. It's okay to be inefficient when things are mostly idle. And bursts are both a threat and an opportunity, which I will show you next time. The reason for that is when I have a burst, I get queued items that I can rearrange to get better seeking behavior on the disk. Okay, so in conclusion, devices we talked about have pretty complex protocols for interacting and performance characteristics. We talked about hard disk drives, controller plus seek plus rotation plus transfer, and SSDs with controller plus transfer, but you got to worry about them being erased and worn out. We talked about bursts, introducing queuing delays, and we're going to start talking about interesting systems like file systems designed to optimize performance, but the simple thing to remember is locality on disks is what matters. Okay? Disk performance looks like that, and the queuing latency is, this is a more general equation. That sounds like something to put on your cheat sheet, and also understand the numbers. All right, unless there's any questions, I'm going to let you guys go. Have a great Wednesday night.